This is a short summary video of our recent paper. I'm Tom Goto at National Tsinghua University. This work was done in collaboration with Goto and Toft at the Cosmology Center. Dark energy is one of the biggest mysteries of the modern astronomy and physics. And we think one of the next key questions is if the dark energy is time variable or not. In terms of the equation of the state, this WG parameter is 0 or not. And to probe the variability, it is important to probe at higher redshift because it's a variability, it helps to investigate a long time span. For example, in this Hubble diagram, those models, cosmological models with time variable dark energy equation of state will have larger difference at higher redshift 2 and beyond. However, type 1a supernova are less useful at high redshift because even type 1a supernova become too faint to be observed with the modern telescopes. And more fundamentally, there's a long time delay before the type 1a supernova reaches Chandrasekhar mass and explode. It takes about a few gigayears. So when the age of the universe is less than a few gigayears, there won't be any more type 1a supernova. So we need a brighter standard candle at higher redshift. So what we focused is millimeter galaxies, which are being observed with ALMA. These are examples of millimeter galaxies detected with ALMA at redshift 6. So what we did is we compiled large sample of millimeter galaxies detected in CO from the literature. And I created a large sample of CO galaxies. And what we found is a correlation between CO line luminosity and then CO line width. This black line is the best fit power law with the best fit parameters like this. And then the slope, the positive slope, is at 8.7 sigma. And these blue lines connect the median. And as you can see, the line width increases with increasing CO luminosity. And also, correlation coefficient has very, very small p-value, which means the correlation is very, very significant. So I think we can conclude we found a weak but very significant correlation between CO luminosity and line width. The scatter around the best fit power law is 43%, which is consistent with what you expect from a thin, randomly oriented disk. This finding is not very surprising because at low redshift there exists Terry-Fisher relation. Terry-Fisher relation is a correlation between rotational velocity of spiral galaxies and then luminosity of spiral galaxies. And then we use this method to measure distance in the local universe. And then the correlation between line luminosity and then line width of CO we found can be considered a high redshift version of this Terry-Fisher relation. And we investigate if there's a redshift evolution on this relation or not. These red points are high redshift sample at redshift greater than 3 among our sample, and then blue points are some of the galaxies are redshift less than 3. And then best fit lines to each sample, best fit power law to each sample is shown in these lines, and then those two lines are consistent to each other. So at least within our sample, there's no sign of redshift evolution. If there's no redshift evolution, we can use this correlation to measure luminosity distance to some millimeter galaxies. For example, we can measure the line width from observation. Then, assuming this relation, we can estimate the CO luminosity of that submillimeter galaxy. And then by comparing this estimated luminosity to observed flux, we can measure the luminosity distance to submillimeter galaxies. by this method, we created a Hubble diagram. And these are our data points. And at the moment, unfortunately, the scatter is too large to conclude on any cosmological models. However, the situation will improve in the near future. Because ALMA is rapidly detecting more and more sub-millimeter galaxies, the number of the sub-millimeter galaxies will increase in the near future. And at least random noises we can beat with statistics. And ALMA also has very high spatial resolution. For example, 0.037 arcseconds in band 3 at the extended configuration. This is 0.2 kPa even at redshift 6. So ALMA can resolve sub-millimeter galaxies, and this will bring crucial information on inclination and if the source is gravitationally magnified or not. So in summary, by comparing large sample of CO galaxies, we found a weak but very significant correlation between CO luminosity and line width. And this relation has interesting potential to be used to create a Hubble diagram at very high redshift.